Welcome to AI with Sally, a podcast that takes a closer look at some of the most interesting technology stories on artificial intelligence and machine learning. We'll hear about the latest in hardware and software that has a big impact on the world of AI. I'm your host, Sally Ward-Foxton. Welcome back to AI with Sally. This episode is sponsored by 4DS Memory, and we'll be hearing from 4DS Chief Strategy Officer Peter Hyams later in the show on their ReRAM technology. It's called the memory that breathes. But first, here is some AI news you might have missed from eetimes.com. New MLPerf inference scores are out. This round we got the first scores for AMD's much anticipated MI300X. It managed similar results to NVIDIA's H100 to within 3 or 4%. But compared to the H200, which has more memory than H100, AMD is more like 30 to 40% behind. We also got the first results for NVIDIA's Blackwell, the B200, which has double the compute, more memory, and more aggressive quantization than for Hopper GPUs. And we saw new challenger Untether enter the fray with their inference cards. They only submitted results for ResNet 50, but they really shine on power efficiency, about 3x the queries per second per watt versus NVIDIA H200. If you want to read my full summary of the results, head on over to eetimes.com. British IP company Imagination has rebooted itself over the last few years, and in the last 18 months, it's rebooted its AI strategy. The company had 3 generations of neural network accelerator IP, which it's decided to discontinue about 18 months ago, citing huge challenges with an ever-evolving software stack and in supporting customers' specific workloads. They've decided instead to focus on their existing GPU lines, and they have some strong arguments why AI in edge devices is a good fit for the embedded GPU. You can read more in my interview with Imagination's Chief of Engineering at eetimes.com. Korean AI chip startup Furiosa picked Hot Chips to unveil its second-generation data center inference accelerator, Renegade. I had a long chat with CEO June Pike about the new product and the company's origins and vision. The company's tensor contraction processor concept is a non-Matmul architecture that treats the tensor as the primitive rather than splitting them into 2D matrices for processing. There are more details at eetimes.com. 4DS Memory is bringing high bandwidth, high endurance, non-volatile memory to advanced CMOS process nodes. Its technology, known as interface switching ReRAM, features tunable persistence and low energy per bit, which I think will be a great match for AI processors. I sat down with Chief Strategy Officer Peter Hyams to find out a little more. I started by asking Peter to give us an intro to ReRAM, and we got talking about the technology's suitability for AI and what the potential might be for AI systems in the future. Okay, Peter, welcome to the show.
Thank you. I'm so glad to be here.
So, Peter, you're with 4DS. You're working on ReRAM. Maybe we could just start right from the beginning. Maybe you could just tell me a little bit to start with about what is ReRAM, actually.
Yeah, sure. So there's a whole field of emerging memory technologies that have been in development for the last 10 or 15 years to help the industry move beyond the limitations of traditional flash technologies. And flash has worked well for many, many years, but there's issues with being able to continue to use that technology as you scale to smaller and smaller geometries. So advanced or emerging memories is kind of this general field. ReRAM is one of the different types of memories that are in there. Others that you may have heard of is MRAM and phase change and FERAM and other kinds of things. ReRAM stands for resistive memory. So it is essentially programming the cell between a high and a low resistance state in order to program the 1 or the 0. So it's a very simplistic way of looking at it. And there's different ways of approaching it. So we are pursuing one, which is based on a material called PCMO, which I guess we'll talk about in a minute. And the others that are out there use a different kind of an approach called filamentary. We'll talk about the differences as well.
So with ReRAM being a type of persistent memory, maybe you could tell us also how persistent memory is going to be particularly good for AI in particular.
Yeah, so persistent memory is something that has been talked about in the industry for 10 years, again, or more. And it's this idea of having memory that works as fast as DRAM but has that persistence. So it holds on to that data for a long time relative to the central processor units. And this is something that was really promoted by Intel with their Optane technology. And they had a number of different applications for it, but the main one was kind of like a tiered memory approach where this persistent memory could be as a backup to the DRAM and SRAM, which is the main dynamic memories that these processors use, and allow them to have this kind of a backup and retention and fault tolerance that some of these systems needs. Optane didn't fulfill all of its promises, I guess, because of different commercial and technical issues. But we think that there's still a need. We still see people talking about it in the industry, and we think that the memory technology that we're bringing to market can really fit that need. In terms of how it actually can help, so this is for persistence. It can help with these AI systems in terms of being able to provide that backup and recovery and storage and retention of the data during these processing needs. There's other potential applications where you can use this persistence in order to store these weights for all of these vector multiplication, and that's something that different people are trying to do on an analog basis with these different types of memories.
So what's different about 4DS or 4DS's approach to ReRAM? How it's a kind of slightly different flavor of ReRAM that you're working on?
Yeah, sure. So, and this is what I mentioned before or touched on before. So within the ReRAM area, there's two main approaches to it. The traditional one is using something called filamentary, where you're actually forming a filament or a wire of atoms or ions through this oxide film in order to create this low resistance path. And that, there's commercial ReRAMs out there, that do this, and it does give them the retention. The drawbacks are in terms of the energy of writing, the speed of the writing, and then the endurance of that kind of a cell, because you're forming and breaking these filaments or wires on a constant basis. Our technology is different. It's still ReRAM in terms of being able to program a higher or low resistance state, but it uses a different kind of physical mechanism. And this is using a material which is called PCMO. It stands for the elements in it. And it's a type of a piezo kind of a crystal that has some unique properties. So like any other piezo, it can conduct a current, but the O in the PCMO is oxygen. And so that oxygen can be removed from the lattice or injected back into the lattice. And it's that oxygen that really supports the current. So we call this an interface switching technology because that oxygen removal happens at the interface between the top electrode and this PCMO. And because that actually works very fast. So because it's a very fast process and it is something which is spread over the entire area of that top cell, the speed is very fast and the endurance actually stays quite high. So we can still get the good programming in terms of high and low resistance states, but we can do it with the technology that's much faster than the other ReRAM and gives much higher endurance. And that's why we think that it's really significant for the industry right now, because there's, like with this work on persistent memory, there's been a growing recognition that there needs to be a new memory technology that can work as fast as DRAM, but offers these characteristics of persistence and retention and endurance.
So it's a completely different physical mechanism, like it's just a different material and a completely different material approach.
Exactly. Yeah. This is something actually that has been of interest to the researchers for many years, but it's really stayed more in the academic space. 4DS is the only company that has been developing this PCMO approach towards commercial viability.
So all the properties that you mentioned sound really attractive for all different kinds of systems, but for AI systems in particular then, not just persistence, but the other qualities you mentioned can be useful for AI as well, right?
Yes, that's right. So when we look at where are the challenges with these AI systems, a lot of people talk about this memory bandwidth limitation, which is, where is the data located? How fast can you get it into these processors? How much energy does it take to store them back into the memory systems and those kinds of things? So current architectures have a lot of tricks that they use. New processor architectures are trying to load as much SRAM into these chips as possible. So you get companies that are actually, developing chips that are wafer scale. So true, huge processor things, just because the current philosophy is keep as much of that, keep all of that data with the GPU as much as you can, and then you eliminate the need to have external memory. Obviously, that has some limitations with these large language models getting huge and more and more parameters. So we think that there's need for new technologies that can offer different architectural choices.
Yeah, I think energy efficiency is going to be particularly attractive as well. I mean, you talk about wafer scale systems, but these are massive, massive systems that are massive, like kilowatts systems, or megawatts of power. So yeah, energy efficiency, I think, is going to be really important, right?
Yeah, for sure. Yeah, and that's one of the advantages that you get when you have a very, very fast programming speed is low energy per bit, because it goes directly with time, right? In terms of how much you program.
So AI accelerators that we're talking about use some combination of SRAM and DRAM today, or some combination of SRAM and HBM usually. How does ReRAM fit in? Are we talking about replacing DRAM here?
No, it's more of a complement, I would say,
okay.
As well as to SRAM. I mean, SRAM is very, very fast, and that's why people use it. But this is also a very big cell, in terms of the space that it requires, because it's 6 transistors in order to do this kind of architecture. It would be great if if there was a way that people could use 4DS in order to replace SRAM directly, but it has some unique properties which probably will mean that people will continue to use it. But there needs to be backup, there needs to be recovery, there needs to be a way to have this kind of a tiered memory, like I'm talking about, in order to have that completely integrated solution for these AI models that includes the backup, the recovery, and the fault tolerance that you get with a persistent memory solution. So a complement to DRAM and SRAM.
Yeah, I guess like just another kind of level in the hierarchy where we already use SRAM and DRAM for the different properties in different ways. So just an addition to that hierarchy, I guess.
Yeah. Cool. I mean, one of the things that you get with persistence is that, that data doesn't have to be refreshed all the time. So, this is where, DRAM is used because it's very fast, but it also has to be refreshed constantly because it's a volatile technology. So, if you can have a technology like 4DS where you can retain the data for, minutes or hours or days, and, for these large language models where that data needs to be available but doesn't change on a constant basis. So this is one possible application where persistent memory, can give you some advantages as long as it continues to work at the same speeds as DRAM, which ours does. Then exactly right that you'll be saving on the energy side by having a more of a persistent approach as opposed to the traditional DRAM approach.
So Peter, I know you've been working with IMEC on this technology. Tell us a bit about the nature of that partnership.
So IMEC, as your readers probably know, is one of the leading advanced semiconductor technology development houses in the world. They're in Belgium. And we have a good, strong relationship with them. They've been our manufacturing or process integration, process development partner for the last 5 or 6 years. I'm not exactly sure when it started, but in that time frame. And they continue to be our partners. So the current runs that we have in terms of improving and developing our technology, do run through IMEC as our partner for this stuff. We have lots running through there right now. So the focus this year is on 2 things. One is, all the previous results that we've done are based on a 60 nanometer cell. That's 60 nanometers on a side for the PCMO element, if you will. So the focus for this year is on, improving that and showing the repeatability and also optimizing that process. And then secondly, and most importantly, is scaling that down to 20 nanometers. 20 nanometers is the scale that we always had as our target in order to get to memory density that is truly competitive in the market. And as you know, for all memory technologies, it's all based on die area really drives the economics and of course the density. So if you need to get to gigabit level memory solutions, then you need to have something down at this scale. And so that's also running through this fab right now. So we're very excited to have those lots come out of fab so that we can analyze the results, which we should be able to see some of those results towards the end of this year and the beginning of next year.
I was going to ask, how far along are you really with productizing this? Because when you say we're talking about working here with IMEC, to me, it sounds like research. So I guess I wanted to ask, how far along are you with development and what form might productization take?
Yeah, great question. So this is the other goal for 4DS for this year. So we knew that we had great results on the 60 nanometer cell from last year, and this is what we've been talking about all this year. So our goals for the year really are twofold. One is, of course, the refinement of the process and getting down to 20 nanometers with IMEC. But secondly is really to begin to open the conversations with potential partners. 4DS is a memory technology company. So our role is in developing this technology and proving that it can work and characterizing it, for the applications. But we believe that we need to have a partner in order to take this to the next step in productization, which means coming up with an actual memory cell targeted for a specific application, and to work with them on developing the test chip or the memory cell architecture in order to actually prove it out in a specific application. Excuse me. And that memory cell could be application specific. So how it is architected for an AI system might be different than an embedded edge system versus MCU kind of an application, I suppose. So there's different possible applications for it. So this is really where the conversations need to start.
Yeah, I mean, we're saying AI kind of broad strokes here, but I'm sure everybody that listens to this program will know that AI is absolutely everywhere now. So talking about data
everything from voice recognition all the way through these large language models, right? So
yeah,
it really encompasses the entire span of different processor architectures. So obviously, we think that we have a good solution for the high-end one where you need to have that persistent memory at DRAM speeds and the high densities, but speed, density, energy efficiency, endurance. I mean, these are attractive qualities for many different applications. So very interested in continuing to have the conversations that we're doing and looking at the different possible applications for the technology.
I mean, literally all the way down to IoT, kind of microcontroller level of applications here. I mean, I feel like the requirements, I mean, everybody loves energy efficiency, but I feel like the requirements from that kind of system are quite different. But you're saying you fit in there as well, right? Yeah,
sure. This is kind of one of the truisms, I guess, of technology in general and semiconductors is that, your design complexity will expand to fill the available space that you give it, right? It's kind of the analogy of the old computer models, computer architectures, right? I remember when Bill Gates used to say that, no computer would ever need more than, I forget what he was saying, 64 kilobytes of memory or something like that. But, give people more memory and they'll fill it up with different applications. So I do believe that obviously for edge type applications or IoT applications, size and cost and especially energy efficiency is really, really important. But, given those parameters, if you give the designer more space or more processing power, then they're going to use it somehow. It's going to be more sophisticated and better solutions.
But it's a matter of developing a specific type of cell for each of these different applications based on the same material. Am I getting it right?
Could be, yeah. Like I was saying before, there's different architectural choices for how the memory could be used. The actual memory itself would be the same, but it's how you hook it up. Are you writing it, just bit-wise, or are you doing it word-wise or page-wise? I mean, this is kind of, you look at DRAM architectures. I mean, that's how they get the high bandwidth, right? Is they do this massively parallel write sequences. So not sure that we can be, as wide and as high bandwidth as some of that DRAM architectures, but why not? I mean, we want to explore that with the right partner.
Once you have partners, then what kind of timeline do you think we're talking about for getting this out into the market or into devices and applications?
Yeah, I think practically speaking, we are with IMEC right now. We're getting our 20 nanometer cell and other runs out this year, and we'll be testing those, improving our work on those vehicles. But yeah, I think with if you get a partner and then you work together and coming up with a test chip or a memory cell architecture, it's still going to be 2 or 3 years before something is out and ready, to be used in the marketplace. So the ideal type of partner for us and for your listeners, or to consider, is somebody that is really looking at that, 2 generations out architectures or technologies. I mean, this is something that we think as I said, can complement the current memory solutions that are out there. It's a new version of a tiered memory solution, but it's not a drop-in replacement for anything that exists today. So, the ideal partner is something that one is trying to figure out how to get around the current bottlenecks that they currently have based on the technologies that they have to use today, and are looking for something with different kinds of capabilities. And that's what we're offering to them. And that's really where we see it going.
Further into the future, though, I know you said you're working on a 20 nanometer cell next, but maybe 5 to 10 years into the future, what's for this technology, do you think?
It could conceivably continue to scale down lower. This is going to be application driven. And if there's a real need for it to get to lower and lower scales, because there's always a trade-off, right? As you scale things down, then you're also scaling down the currents that you're getting. It makes the sensing of the cells more tricky and more difficult. So, and you have to ask, what is the nature for how much density you actually need. So most likely it would not scale in that dimension, that XY dimension. If there was a path towards higher density for this technology, it would be in the vertical dimension. So instead of having a traditional pass gate or transistor type of an approach, you would have a true crossbar with the selector kind of an approach that would allow you to have, to integrate these memory elements vertically and really take advantage of the ability of the rest of the transistors, the rest of the circuitry to scale. Because this is 20 nanometers for the cell, but it's going into an advanced CMOS node technology anyway. So those will continue to scale. So the memory has to be able to adapt to that.
What about, you said crossbar there, so obviously my ears pricked up. What about using a memory array to do more like a compute and memory type scheme for actually using memory for computation? Would your ReRAM fit that kind of application maybe in the future?
Yes, sure. I think it could. It could be used in either as a persistent memory for that memory storage or as a backup to the SRAM in that configuration. So, actually the traditional, the original Optane persistent memory was a crossbar kind of a architecture as well, as you recall. And that was done for density and for cost and scaling purposes. So for sure, that same economics and dynamics would be applicable to 4DS technology.
Very exciting, Peter. Thank you so much for joining us.
Oh, thank you so much.
Thank you very much to Peter Hymes, Chief Strategy Officer at 4DS, for the conversation. This episode of AI with Sally was brought to you by 4DS. Thank you, 4DS, for sponsoring us. That brings us to the end of the episode. Please tune in again next time to hear more news and views on AI, machine learning, and the technologies that enable them. If you're listening to this on the podcast page at eetimes.com, links to articles on topics we've discussed are shown on your left. AI with Sally is brought to you by Aspen Core Media. The host is Sally Ward Foxton, and the producer is James Eade. Thanks for listening.